Hi, welcome back. We're in lecture 19, and now we're up to segment 2, and in segment 2 we're going to cover the chi-square test of independence. So the chi-square test of independence just determines whether there's a relationship or a contingency between two categorical variables. So the example I'm going to use is this election polling example, where we're going to look at the relationship between the gender of the voter and their preference among candidates for the New York City mayoral election. So again, let's assume a small poll, this time a little bit bigger than the one we looked at in segment 1, but still just 200 likely voters. That's considered small. And just to make this interesting and to show you how the chi-square test of independence works, we'll look at a poll that has more males than females. I did this on purpose just so we can see a little bit more about how this test of independence works and make you think about the contingency table. Again, we're just going to look at whether the likely voter is intending to vote for Quinn, Loda, or some other candidate. Let's assume these are the results that we observed. So again, remember there were more male likely voters in this sample. So what we see is in the men, 90, 40, and 10 going across Quinn, Loda, and other. So again, looks like more people prefer Quinn. And then in the female voters, it's 40, 10, 10. But the question we're asking here is there a relationship between the gender of the voter and which candidate they prefer? It's a little difficult to eyeball this table and see because we have so many more men than women. And that's exactly why I did that in this example. So let's go ahead and do the actual calculation and get a p-value and see what happens. So again, the null hypothesis is that there's no effect, so there's no relationship between voter gender and voter preference. The alternative hypothesis, of course, is that there is a relationship. There's a contingency. The chi-square formula is exactly the same as the chi-square formula we saw in the last segment for goodness of fit. Degrees of freedom is slightly different because now we have rows and columns, so it's number of rows minus 1 times number of columns minus 1. The p-value, again, is determined by the chi-square value and degrees of freedom, and that comes from that family of sampling distributions of chi-square that looks like this. Again, that's conceptually analogous to the family of t distributions, the family of f distributions. So again, we get our p-values from the actual value and degrees of freedom. Again, we want to estimate effect size to supplement that NHST and p-value. Again, it's Kramer's V or phi, and we looked at the formula in the last segment. Again, we'll do that for this example. The only trick here, and we'll just do this once in a hand calculation going forward in lab, and beyond that we'll do this in R, but we can do this calculation by hand. We just have to calculate the expected frequencies in all rows and columns, and because there's a different number of males and females in the sample, that's a little bit tricky. So to compute the expected frequencies, we're going to calculate the number of people in the sample in a row over the total number of people in the sample, multiplied by the number of people in a column. Now let's look at that in the table. So our row totals are here. There's 60 females total, 140 males total, and our column totals are 130, 50, and 20. So I can do my expected frequency counts. It's just total number of people in a row over the total number of people times total number of people in a column. So I've done that for each cell. If you look across the first row, I get 39, 15, and 6. You look across the second row, we get 91, 35, and 14. So now I'm ready to do my calculations just like we did in the last segment for goodness of fit. I've lined up all my observed frequencies, then I've lined up all my expected frequencies, and I just get the difference, then square each different score, and then sum all those squared different scores, and that's my chi-square value. So in this example, the chi-square value is 6.23 with 2 degrees of freedom. Turns out the p-value associated with that is 0.04. So here we can say that there is a statistically significant relationship between the gender of the voter and who they're likely to vote for. If we look back at the contingency table and the actual results, note that it's really coming from this piece of the table, right? The expected frequencies here are 15 and 35 for load up, but they're 10 and 40 is what we observed. So what's really driving this result is that more men are choosing LODA than we would expect. So in this case, we get a statistically significant result. Again, we can test the effect size. You can see we just barely crossed the threshold into statistical significance. So if you look at the effect size, it's not that large, it's 0.18. So it's still a very modest effect, but this time, relative to the example we did in segment 1, this time we managed to get it to be statistically significant, but the effect size is similar to the last one we looked at. Again, let's look at how we would do this in R. Your data frame would look something like this, where you have the information for each voter represented on a row. What we need to do is use that table function in R with our election data frame. We're going to create a table of candidate by gender and then do the chi-square test function on the observed values. I did that in R just to check my work, and I got the chi-square value that we got when we did it by hand. That's 6.2271. We got degrees of freedom 2 and p-value of 0.04. So yep, statistically significant, matches the results we got when we did it by hand. Finally, there are a couple of assumptions associated with the chi-square test of independence. First, there's an assumption that you have adequate expected cell counts. So a common rule is 5 or more in each cell in a 2x2 table, and 5 or more in 80% of the cells if we have larger tables. When that assumption is not met, people typically apply Fisher's exact test, which is a non-parametric test, which we're going to talk about in next week's lectures. And I'm going to actually cover Fisher's exact test as one of the examples of a non-parametric test when we get to that topic. The other assumption is independence. So the voters that are observed in one category have no influence over voters that are observed in other categories. So chi-square can't be used to test correlated data, so matched pairs or panel data. In such cases, we'll use McNamara's test of dependent proportions. Again, that's a test, it's a non-parametric test, which we'll cover next week. So to wrap up this segment, chi-square tests are used when we're dealing with categorical data. So categorical predictors, categorical outcomes. Chi-square test of independence is a null hypothesis significance test, so we're going to follow that up with an estimate of effect size. The estimate of effect size here is Kramer's V. And the test of independence has 2 assumptions. 1, adequate expected cell counts, and 2, independence.